in our syllabus. So as the title suggests, we are going to talk about place and route for FPGAs. Now, placing and routing is one very important activity. Fortunately, it happens transparently for the designer. Okay, and you don't really have to bother about how it is optimized, because there are so many algorithms which are being used. We are going to see, just have a glance at all these algorithms. If you are interested, you can go into the depths of those algorithms. Okay, so this is the FPGA CAD flow, which we already know. The design entry starts with circuit description, which can be in the form of VHDL schematic or VHDL or schematic, or even the state diagram, as we have already studied earlier. Then you synthesize the logic blocks and finally place the logic blocks in FPGA. Now this is where the physical design starts. Okay. Now this is all done transparently, but you should have at least some information about what is exactly going on inside this particular process. Then you have placement. This is the placement process, and then you ultimately have the routing process to generate. Finally, what is the end product is to generate what is called as the FPGA programming file. Okay, which is actually a bit stream. So this CAD flow, from the perspective of physical design, we are looking at. We're not going into the details of the CAD flow right from the schematic, the VHDL, and then the compilation and all those things, because we have already seen that, covered that particular part. So this is only to emphasize what exactly do you mean by the physical design. So physical design composes of two processes. One is the placing or placement and the routing. Of course, before that you have to complete the synthesis process. So what is placement? What is the goal? The goal is determine which logic block within an FPGA should be implemented. Each of the logic blocks is required by the circuit. Objective, so this is concerned with the placement. Okay, minimize the required wiring. So your basic goal is to minimize the required wiring. That is how you place the blocks, right? Because there are so many different aspects which will come with the physical placement of these logic blocks. Okay, now we are concentrating only on the FPGA. So because FPGA is, we already have seen CPLDs, we have predictable delays, but in FPGAs we don't have such a kind of luxury. Okay, so objective is to minimize the required wiring. All right, then balance the wiring density across the FPGA. Okay, that is called as a routability driven placement. Okay, how you are in a position to route route that particular blocks. Okay, those particular blocks, and maximize the circuit speed. So this is basically one of the most important aspects as to how do you maximize the circuit speed, by simply using what is called as a timing driven placement. Okay, so there are two flavors again: routability driven placement and timing driven placement. There are three major classes of placing algorithms or types of placers. They are called as min cut, that is partitioning based placers, analytic placers, and simulated annealing based placers. Okay, so there are three major classes. Simulated annealing, let us have a look at this. So this actually is an algorithm which is borrowed from, the concept is borrowed from the annealing process used to gradually cool the molten metal to produce a high quality crystal structure. If you have ever understood, or let us say studied, the process of annealing, okay, most of the times iron and copper, these are the metals where this annealing process is used. And if you melt particular, let us say, item, and if you suddenly cool it, then it is quite possible that there will be micro cracks which are generated because of the lattice placement, that is a crystal structure. Okay, so a very interesting process people have found out. I mean, this was actually kind of, even ancient people have found out this process, that if you gradually cool it in a particular order, in that case the crystal structures the molecular structure, they get arranged in such a way so as to give the maximum or high quality kind of output. High quality in the sense durability is there. Okay. Now this was basically used for manufacturing or fabricating the swords that used to be used in the battlefields. Okay, so this process has actually developed. I mean, this particular process was actually developed for making swords and all that, those kinds of accessories like daggers and all that. Okay, now this process actually mimics that process which is called as simulated annealing. Okay, simulated annealing takes an existing solution and then changes this particular solution in a series of random moves. Now it's not totally random, but it has got some certain way in which it has to proceed. Okay, let me just see. All right. Okay, so this simulated annealing will take one solution. It will start with a solution and then evolve that solution into so many different varieties, ultimately giving you the best possible variety. So this is simulated annealing is one kind of optimization tool. Okay, if you contrast it with the genetic algorithms, it will be something like genetic algorithms take a large number of solutions and then try to get the best out of it by mimicking the behavior of evolution. Function, energy function is the test function, for example, and it is tested on. If the test function is having a certain value, if that is decreasing, many times we require the mean square error to minimize. So for example, if that particular energy is decreasing, in that case, if the solution that is obtained by a particular random move, if it is increasing the energy, then we discard it and keep the one which is decreasing the energy. So in order to escape from solutions which are called as local minima, it allows uphill moves that seemingly move to a less desirable solution. So basically, in optimization theory, basically what we have is, see, there are, if you take a particular problem, now this is more relevant when we talk about artificial neural networks and all that, which happens to be my area of specialization. We have a solution, or we have possible solutions or possible answers. Okay, and what we have to do is we have to select the best possible answer. Okay, maybe the best possible answer, which is called as the global minima, is not obtainable in, let us say, a finite number of iterations. Okay, in such situations, a local minima, which is a little bit inferior to the global minima but is acceptable, can also be called as a solution. Now, when we talk about this local minima can be also a solution which is not really desirable. Okay, and it's possible that your process may get stuck in that local minimum. So this particular algorithm is also equipped with a way in for getting out of this local minimum. If it is stuck in the local minima, it will never go to the optimal solution, that is the global minimum. Okay, so it is all based on probability. So probability of accepting an uphill move is controlled by the expression e to the power minus delta E by T, where delta E is the resulting increase in the energy function and T is the current temperature. So this temperature is not really a physical temperature, it is again a simulated temperature. Okay, you have to understand this factor very clearly. Okay, it is nothing to do with the physical temperature. Okay, so if I increase the temperature, a change in the temperature and the change in energy. So just like the annealing process where the temperature is gradually decreased and the energy also has to decrease, in that case, we have to see to it that you get the least energy point. So the temperature is slowly decreased and the system finally comes to a rest. at a low energy configuration. Remember that low energy configuration is the most stable kind of configuration. All right. So this is our expected global minima, you can say. Now, interestingly, how it is used for placement, because we have so many different objectives. Okay. So what kind of placement can be done with this simulated annealing? So we have an initial placement, that is the initial solution, which is the starting point, which is created by assigning logic blocks of the circuit randomly to the available locations in the FPGA. And we already have said that the cost function, that is nothing but the energy function here, is wire length driven placement, which is the sum over all nets of the half perimeter of their bounding boxes. Okay, so this is all related to optimization. A move can be the exchange of locations of two randomly selected logic blocks. So you simply swap the locations of the blocks and check the energy function, that is your cost function. And if it is less, go ahead with swapping other blocks. Otherwise, you have to retain that particular configuration and try some other solution. Okay. So initially, temperature T is very high, so almost all moves are accepted. Okay. It is gradually decreased as the placement is refined, so that eventually the probability of accepting a move that makes the placement worse is very, very low. So it is all probabilistic. Like, as I decrease the temperature, I will decrease the threshold, for example, as to how I will, whether I will select or reject that particular move. An advantage is that it is easy to add new optimization objectives, or those are also called as constraints. But the drawback is the running time required. Remember that this will take finite number of iterations, and that number is again a very big headache. It can take a few minutes, or it can take a few hours, or it can take a few days. As we said, it is probabilistic, or it may never converge. Okay, that also is a possibility. So this kind of placer is having a drawback of the number of iterations, and of course it translates into the running time that is required. We have the next type, that is a min cut placement. The given circuit is repeatedly partitioned into two sub-circuits. Chip area is partitioned alternately in the horizontal and the vertical directions. Each sub-circuit is assigned to a subsection. This process will be repeated until all the sub-circuit consists of a single logic block and have unique solution on the chip area. So this is just divide and rule kind of thing. So go on partitioning and ultimately find out whether your parameters, your objectives are met with or not. During partition, the number of nets that are cut by the partition is usually minimized based on intuition. So this is more or less a heuristic kind of an approach. So this is one interesting approach. Okay, this is a just simulated annealing based placer algorithm. You can just have a look at it. So it begins, you have a random placement and initial temperature, and there will be some exit criterion. Until that particular criterion is not met with, you have to go on having iterations. So you can see here that to generate via move, and you can just check over here whether that cost function, that delta is less than 0 or delta is greater than 0, again with probability e to the power minus delta by t, and then finally you can get out of the algorithm. So for those who want to really go into this kind of study, they can go into the details of how you can have solutions to such kinds of problems. Okay, this also is a lucrative career direction, where it is almost you can just, of course, a research area also, where you can come out with a novel solution, a novel algorithm, which can be used for placement, and you can just patent that algorithm if you want. Then this is how the partitioning methods. The commonly used partitioning method is to it's the iterative improvement approach that makes the local change to an initial partition. There is something called as KL approach, Kernighan and Lin. They proposed a graph bisectioning algorithm which starts with a random initial partition and then uses pairwise swapping of vertices between partitions. until no improvement is possible. Okay. Now there is something called as a greedy algorithm, which is generally used for finding out the least possible path. Okay, the shortest path. So that is called as a greedy algorithm. You can just have a look at the greedy algorithm elsewhere. You will find a lot of literature on that. Now this is used as one of the parts, and it will accept a move only if it provides immediate benefit. But such kind of short-sightedness often leads to what is called as local minima, from which the algorithm cannot escape. Scale algorithm was designed to able to escape from its local minimum. So there is this competing algorithm called as greedy algorithm, but then this greedy algorithm has got some problems. Earlier, people used to use greedy algorithms only, but then they found out that it gets often stuck into the local minima, okay, which may not be acceptable. So this particular algorithm was designed to escape from that local minimum. This is, you can see, just have a look at this. Let us not go into the details, because this is again going into the optimization theory arena. Okay, but just look at it. We'll say that G is the initial partition. So we start with bisectioning, that is partitioning it into two, A and B with small cut cost. Then partitioning G into A and B such that the vertices, okay, there is a minimum distance between the vertices BA and BB, okay, and you repeat that procedure, compute the cost reduction for moving these vertices, find a pair of unlocked vertices VAI, which belongs to VA, and BBI, which belongs to BB. VA and BB are sets of vertices whose exchange makes the largest decrease or smallest increase in the cut cost. Okay, and then mark VAI and BBI as locked, store that gain function, and compute the new cost. Okay, now you find out K for all such partitionings. If GK is greater than 0, then you move this, interchange this, otherwise you lock it and get out of the algorithm. So it is again based on a different approach, mostly the swapping or interchanging of the vertices. This is the KL algorithm explanation. So one pass of this KL algorithm, vertex pairs which give the largest distance decrease or the smallest increase in cut size are exchanged. These vertices are then locked, that is, they are not allowed from participating in any further processing. This will continue until all the vertices are locked, that is finalized. And if there is no such K that GK is greater than 0, then the current partition cannot be improved. So this is a stopping criteria. So the algorithm will terminate. Otherwise, another K is chosen so that it maximizes GK and makes the interchange and continues with the iterations. So this is called as the KL algorithm. There is something called as the fiducia matrices algorithm. So this KL algorithm partitions a circuit modeled as a graph such that cost is minimized. But FM, that is fiducia and matrices, takes into consideration multiple terminal nets and the size of the circuit element. So this is a much more pronounced, advanced kind of algorithm. The features, we are not going to go into the details of this algorithm, only the features that we are going to see which are different from KL. Reduce the number of nets cut instead of number of edge cut. Okay, only a single vertex is moved across the cut in a single move, and vertices can have different sizes. So this is much more advanced. It can handle uneven partitions or uneven sized partitions. There is something called as a balance factor which is introduced. A special data structure is used to select vertices to be moved across the cut to improve the running time. So this is a much more improved version of the KL, and which is mostly preferred in many of the placers. And there are something called as analytical placers. Now these make use of numerical techniques to compute the coordinates. Okay, it is often based on what is called as a quadratic wire length objective. So again, there is an objective, and if the connectivity matrix C, which is the Cij, represents the connection between logic blocks of the circuit, then minimizing this is the, whatever you see here is the is the cost function. Okay, so you have to minimize this cost function where xi, yi is the coordinate of the logic block I and the layout area. Again, you can use a lot of numerical techniques which are well suited for this kind of minimization. These are called as analytic placers. Then if you look at the specific FPGA specific placement issues, the number of routing tracks in routing channels are fixed on FPGA. Necessary condition for a good solution is that the channel density cannot exceed the number of routing tracks which are available in the channel. So in order to calculate, these are the actual challenges. Okay, in order to calculate the channel density accurately, some simulated annealing based placement algorithms also perform global routing iteratively for every move. So not only local placement, but they also have to think about, or let us say to work out the global placement, global optimization also. So an FPGA will contain routing tracks of various lengths. This is one more problem. Simple interconnection delay estimation model based on net length or fan out are not accurate enough, specifically when we want to have timing driven FPGA placement algorithms. Okay, so this is one important aspect. Fast and accurate interconnection delay computation methods are needed for doing the timing driven placement. Okay, so that is all as far as the placement is concerned. Let us have a look at the routing. Okay, just a minute. Okay, once the locations for all the logic blocks are selected, the router will assign nets of the circuit to the routing segments. Now, please remember the difference between placement and routing. Placement is concerned with the optimal placement of the logic blocks, whereas routing is concerned with the actual connection between these logic blocks so that we have optimal solution. Okay, so a router assigns net circuit to the routing segments and determines which programmable switches should be turned on to connect the logic blocks as required by the circuit. Again, since we have a high complexity involved in routing, it is usually performed in two phases. One is called as a global routing and the other one is called as a detailed routing. What is a global routing? It finds for each net a routing tree by selecting a set of channels, routing channels, but does not choose specific routing tracks and switches for each net. That is done in the detailed routing. Since routability is the most important issue, minimization of this density of routing, that is the number of wires specifically, if you like to call it that way, is normally the optimization objective which is used for the global routing. Now, to estimate the routability more accurately, connectivity architecture details within the channel intersection are also to be considered, obviously, because channel intersection areas are usually not fully populated with the switches. So you have to consider the architectural details specifically within the channel intersection areas. Then the next phase is the detailed routing. This will assign each net to specific routing segments in the channels with the constraint of the global router. Okay, design of this detailed algorithms heavily depends on the architecture. For example, detailed routing algorithms for row-based and symmetrical array-based architectures are significantly different. So, depending again on the internal architecture of the FPGA, okay, this kind of detailed routing may change. Now, this is for detailed routing for row-based architecture. Routing channels in row-based architectures are what are called as they are segmented. Okay, routing track in the segmented channel is divided into several segments, and we have switches between the adjacent routing. In the row-based architecture, crossing between the vertical and horizontal segments are fully populated with switches. This is by design, okay, so that any vertical routing segments can be connected to any horizontal segments. So, detailed routing in row-based architecture is reduced to a segmented channel routing problem. Okay, so it is much more easier this way, used with the row-based architecture. So here it is seen. This is a row-based routing architecture. the crossing between vertical and horizontal routings are actually populated with fully populated with switches. Now this is concerned with the actual hardware design of the FPGA itself. All right. So you can have the vertical segments and you have the horizontal segments, and it is easier to route it this way because switches can introduce significant delay due to high fuse resistance. Number of switches allowed for completing a net connection is also restricted. So you have to not only see to it that the length is minimized, but at the same time the number of switches that come into picture in a particular length, they also have to be minimized because each of the um, switch will provide some kind of resistance. Okay, though it is very small, it may accumulate with number of switches and you may have timing issues again. K segment channel routing requires that the maximum number of segments used for routing any net connection be limited to K. For K equal to 1, the K segment channel routing problem can be solved very efficiently using what is called as a bipartite matching methods. If K is greater than 1, the problem becomes non-polynomial time hard problem. NP means non-polynomial time hard problem. What is NP? If you look at the definition of NP, it simply means that you can have a problem, but it cannot be solved within restricted or finite time. Okay. So, for example, using conventional methods, hard computing, that is, if you try to teach the computer, if you try to write a program, computer program to, let us say, uh, recognize a face using the image, it becomes an NP hard problem. Okay, so it may not give you solution within a finite time, and that is the reason why people go for soft computing methods, which is now called as artificial intelligence, and so on. Efficient heuristic algorithms are used to solve this kind of channel routing problem. This is for symmetrical array architecture. The crossing vertical and horizontal routing tracks in symmetrical array based architecture are not fully populated, as in contrast with the earlier type. So therefore, detailed routing for symmetrical array based architecture cannot be reduced to individual channel routing problems. Commonly used approach is to explore the connectivity within the routing channels specified by this global router first, and then using some path search technique. Contention for limited routing resources between different nets always necessitates rip up and retry or reroute in the process. So there is a process called as rip up and retry or reroute. Okay. So many times it is an iterative process wherein if there is a contention, you have to the algorithm has to remove those connections and try again. Okay, that is also there. In fact, these algorithms are mostly used if you have used auto routers in case of printed circuit boards layout design, PCB layout design. There are tools which give you auto routing. Okay, for example, Altium designer is there, or even you can have some other tools like Altiboard, okay, or CAD. All these are equipped with these kinds of routing algorithms. Then interestingly, we have to have what is called as the interconnect delay estimation. This is all the report that will be generated once you fit your design, place and route inside the FPGA. Okay, this is what is the final report that you're going to get. So delay estimation is going to be another important aspect. The capacitance and resistance are definitely responsible for such a kind of delay. Now, which kind of capacitance? How does capacitance come into picture? One, you have the parasitic capacitance, okay, and the other thing is the switches that are being used are mostly the variants of MOSFETs, and all of you know that MOSFET is actually nothing but at the gate terminal you have a capacitance, okay. So this capacitance will come into picture over there. And researchers have modeled nets routing as a RC tree. So as you can see, this is a pi model for a switch, for a wire or an on switch. So you can see here R C by 2 C by 2. This is a model, okay. and Elmore delay, okay, for a sourcing path P is given like this. So what you can do is, I mean, basically it is dependent on the resistance at that particular point and the capacitance of that subtree. Subtree in the sense as it is, you are having an input to a multiple, let us say, branches. This is an RC tree for nets routing, as you can see here. So it starts here. So this actually is modeled as this pi type, so many pi sections taken together. Okay, so it starts from A, B, C, and so on and so forth. So A block to B block, again A block to C block. So you have a lot of such models available. So timing analysis can determine how fast a circuit will operate and help to guide the timing driven CAD tools. So once we have the routing, okay, we can estimate the delay. Okay, and this delay can also be used as one of the objectives. We want to minimize the delays, so it can also be used to minimize when used to go for the routing. Just a moment. Okay, the longest path delay among all combinational paths will dictate how fast a circuit will operate. In fact, we have already seen this longest path delay. A timing graph can be used in timing analysis. The minimum required clock period can be calculated in order, that is order of n time for timing graph and n nodes by traversing the nodes in topological order. First nodes with incoming edges are labeled with arrival time of 0. So a node I can be labeled if all nodes j from which is receives the input have been labeled. So this is an equation which gives you the possible delay. So largest arrival time of all nodes is the minimum clock period required. This is the timing graph which you can have from one LUT to the other LUT. You can see here that this is how the placement of the routing and the placement of the blocks can affect the total timing delays. Okay, the slack of a connection is the amount of delay. So what is a slack? It is a connection is the amount of delay that would be added to this connection without increasing the minimum cycle time. Slack of each connection can be computed so that it is sort of a guideline for timing driven placement and the routing tool. So it is another input parameter for the placement and the routing tools. The required times of the nodes can be computed by traversing the node in again reverse topological order. First nodes with no outgoing edges are labeled with required time of Dmax, which we have already calculated in the previous step. The required time of any node with fan out is computed according to this equation. T required is minimum, where J belongs to all the fan out connections, which is the T required minus the delay. And the slack can be calculated simply as T required minus T arrival minus delay. Connections with a zero slack are on the circuit critical path. So this is basically how you estimate the various timing parameters. And the last part that we are going to have is the partitioning. So in multiple FPGA partitioning, a large circuit is partitioned between multiple FPGA chips. We can also have multiple FPGA chips so that each sub-circuit can be fit into a single FPGA. So you can have a collection of FPGAs if your circuit is huge. In that case, multiple FPGAs can be used. FPGAs partitioning problem are all constraint driven. A partitioning solution must satisfy the input-output constraint as well as the capacity constraint of each FPGA. These algorithms are implemented in commercial CAD tools are mostly move-based approaches. Again, algorithms like the FM, fiducia mathesis algorithms will be used, and that will take care of the FPGA specific constraints. FPGA device is now becoming more heterogeneous in terms of types of resources. Example, wide input gates, SRAM arrays, block memories, or on-chip memories, different types of logic blocks. So the capacity constraints for FPGA can be very complex. So this is basically the idea as far as the physical design is concerned. So again, we have seen the placement, we have seen the routing, and finally the partitioning. Okay, and that is all that I wanted to tell you today. In fact, this completes all every part of the circuit, every part of our syllabus in totality. Okay, I have already given you the handouts. Have you downloaded those, guys?
Yes, sir.
So it is quite exhaustive that way. It is running in about 879 slides. And if you think that you would start reading those and going through those slides just before the examination, it will be a big mistake. So try to regularly go through some part of the material that I have already provided you with, so that it will not be a burden at the ultimately at the end point. Okay, is that okay, guys?
Yes, sir.
Siddesh,
Yes, sir.
okay, all right.